Professor Margaret Reid is going to speak to us on the topic of Einstein versus quantum mechanics. Margaret.
Einstein versus quantum mechanics. Quantum mechanics is our most successful theory, but Einstein wasn't happy about it. He believed it correct, but not complete. So he wanted a better theory. And in 1935, he presented an argument for his case that quantum mechanics was incomplete. And that argument is called the Einstein-Podolsky-Rosen paradox. And this is a story about that paradox. So the puzzling feature of quantum mechanics is the interpretation of the principle of superposition. So in quantum mechanics, if we write a state as a superposition of two other states, then we can't say that the system is in one state or the other until measured. So in quantum mechanics, we learned that if a particle impinges on a two-slit interference apparatus, and there's an interference pattern on the screen, as was described by Hans this morning, then we can't say that the particle goes through one slit or the other. That is the way we learn quantum mechanics. So then the question is, how do we interpret interference with larger particles, like molecules? And ultimately, Schrödinger presented a paradox in 1935 in which he considered the interaction of microscopic systems with macroscopic systems in the absence of external couplings. And he was able to prove that an object like a cat could end up in a superposition of dead and alive states. And then the question is, how does one interpret that? Does one say the cat is dead and alive until measured? So these issues worried Einstein, and they also worried Schrödinger. In quantum mechanics, we know we have the Heisenberg uncertainty principle. So this puts a lower bound on the uncertainty product for position and momentum. And that lower bound is determined by Planck's constant. So in quantum mechanics, no quantum state can simultaneously specify both position and momentum with perfect accuracy. So you might say that maybe the mysteries of quantum mechanics are due to a fundamental microscopic indeterminacy. The point is that Einstein showed that this is not enough to explain the mysteries of quantum mechanics. So Einstein introduced the concept of quantum non-locality. So with Podolsky and Rosen in 1935, he presented an argument for the inconsistency of what he called no spooky action at a distance and the completeness of quantum mechanics. So by no spooky action at a distance, to define this, we consider two spatially separated subsystems. Alice can make measurement on one and Bob measurement on the other. Now, Alice's observations or measurements cannot instantly disturb Bob's system if there's a significant spatial separation. So Einstein was envisaging space-like separated measurement events for Alice and Bob, so that the result or the measurement by Alice does not cause the result of a measurement by Bob. So this is the meaning of no spooky action at a distance, which is the way Einstein presented in popular language a premise we usually call local realism. Einstein's argument was based on entanglement, and in quantum mechanics we define entanglement as when the wave function cannot be written mathematically as a product of two wave functions, one for each subsystem. So in quantum mechanics, entanglement or entangled states have a very special connection, and this has a physical consequence. So this is the entangled state considered by EPR, Einstein-Podolsky-Rosen. So it's a state describing two particles which can be spatially separated. So Alice can make measurements on one particle and Bob measurements on the other, and they can measure x and p position and momentum at each location. This state means that there's a perfect correlation between the positions and also the momentum. So Alice can make a measurement of x at her location, and she can instantly predict the result at Bob's location. Similarly, she can make a measurement of p, momentum, and she can instantly predict the result for momentum at Bob's location. Now, if there's no spooky action at a distance, EPR claimed that Alice's measurement does not in any way disturb Bob's system and therefore doesn't cause his result. So these correlations are magical correlations, because when you think about it, if there's a local uncertainty principle operating at for Bob's particle, and if there's no spooky action at a distance, then these correlations, perfect correlations, become impossible. So this is where the EPR argument was managed to provide an inconsistency between quantum mechanics and no spooky action at a distance. So here's a summary of the EPR argument. The initial premise, measurement by Alice doesn't disturb Bob's system, yet she can choose to predict either Bob's position or momentum. That is the result of his position momentum measurements at his location. And there's absolutely no error in his prediction. So EPR argue that Bob's particle always had a perfectly well-defined position and momentum, regardless of what happened at Alice's location. And this contradicts the uncertainty principle for Bob's particle. So EPR, or Einstein, argued for the incompleteness of quantum mechanics. There had to be hidden variables to supplement the theory. Well, there was a need then to design experiments to test the EPR paradox, because without this special sort of entanglement that EPR talked about, there's no real inconsistency, and there's no need to worry about quantum mechanics and how to interpret it. So the earliest EPR experiment that I'm aware of was by Madame Wu, and based on theoretical predictions by Price and Ward. And Madame Wu is very famous for her experiments on weak interaction. She's probably not so well known for her EPR paradox, but she was the first person to do such an experiment. The experiment done by her, and also a large number of experiments based on John Bell's work, are based on a different sort of entangled state. This is the singlet state of two electrons. But it's realized in the lab in these experiments using photons, single photons on each detector. So these are very small microscopic experiments, and initially they were, because there are more problems associated with interpretation because of detection inefficiencies. Although very recently there's been a lot of progress in improving these experiments, both in Europe and also at Griffith University. So a while ago, I became very interested in the EPR paradox, a long time ago actually, and the original EPR paradox, which was based on position momentum and the uncertainty principle. And, but I never really thought it would be possible to test because of the size of Planck's constant. But then when I was working on squeezed states of light, I became aware that experimentalists like Hans were making measurements on the quantum fluctuation of light. And they had a way that they could detect this in the laboratory. So I started to think about maybe doing EPR paradox with these sorts of systems. So a device in optics is parametric down conversion. This is where you put a pump through a crystal, and you have the emergence of two fields at a lower frequency. So it's like a conservation. A photon is converted to two photons, and there's conservation of energy and momentum. These are at spatially separated locations. So Alice can make measurements on one field and Bob on the other, just like an EPR. Now, it turns out that in quantum mechanics, the wave of a field has amplitudes that act just like x and p, position momentum. and one can write down a Heisenberg uncertainty relation for them. I've written that down here using a scaling of the values, just to simplify the right-hand side. I've scaled the x and p. This is Heisenberg uncertainty principle. And then, so one can evaluate correlations between the x's and p's of each field. And lo and behold, when I looked at that a long time ago, they're just like EPR correlations. The appropriate variances go to 0, but of course this is in the limit of very large pump intensity. So one then also had to work out in a real situation how to get a realistic criterion for EPR. And so I thought back on the argument and wrote down that as long as Alice's predictions are sufficiently good compared to the uncertainty principal product, you can infer an EPR paradox. So the experiments look like this. And the main trick is that there's a local oscillator introduced to combine with the mode with a phase shift that Alice can adjust to measure x or p. And this local oscillator has the effect of amplifying the quantum noise. So it's readable on a screen. And then to compare with the right-hand side, one removes the entanglement and just has a vacuum input, which gives you the basis for the inequality. So by measuring noise reduction, you can infer an EPR paradox by doing sufficient manipulation with the current output currents. So a number of experiments were done, and EPR paradox observed in this manner. So the entanglement shows its noise reduction. So these experiments here are doing better. So with time, the amount of EPR correlation observed has improved. These are all optical experiments, but scientists are now working on systems that have mass, like miniature mechanical oscillators and clusters of cold atoms to detect EPR entanglement. So just finish with a conclusion, talking about the potential applications or the applications of EPR entanglement. So initially we were just interested in the philosophy, but then a new field emerged, quantum information, and EPR turned out to be a very, very useful resource for quantum information tasks. So one of the most well-known ones is teleportation. So this is where Alice wants to send a state to Bob without any degradation or loss of fidelity. Now she can't do that easily in quantum mechanics because quantum mechanics introduces noise, and she can't clone without degradation. But the EPR fields enable her to carry out this process by kind of overcoming the uncertainty principle in a sense. So Alice and Bob share the EPR fields, and this enables Alice to send to Bob a quantum state through appropriate measurements and use of a classical channel. So the final application I think is quite exciting is quantum cryptography, and this will give us security on our communications. And the idea again is the same, similar, that Alice and Bob are sent a sequence of EPR pairs, and they can measure x or p at each location. But because of the correlation, the EPR correlation, they can use that correlation to construct a key. But what is important is that they can also check on a sample of data whether or not the EPR entanglement has been observed between them. If there's an eavesdropper on the channel, then that EPR entanglement is lost. So this is EPR correlation and EPR criteria are a signature of a loss of security of information.
Thank you, Margaret. Are there any questions for Margaret? So, Margaret, these experiments have been made even in the optical fibers, and then in the real systems, you can be able to do that?
Yes, there have been quite a variety of EPR experiments now. As I say, they're all restricted so far primarily to optics, but there's, initially it was just, mostly just they use an optical cavity and the output modes, so the big enhancement of coupling. But there have been EPR fields propagated through optical fibers and the EPR correlations measured at the end of them. Yes. And of
So
course,
that means, in principle, the
Hans
practical
spoke-
systems
yes.
can be possible.
Hans spoke earlier today about his systems, of course.
Any further questions or comments? If not, could you please join me to thank Professor Margaret Reid for a very stimulating talk?